this computer. And now I'm gonna get the slideshow. We're doing pipeline. From chapter 4, the processor. Okay, so in order to understand pipelining, we have to first talk about a metaphor, which is a washing machine setup, or let's say you have to do laundry. Very important to understand this example because we're going to analyze it. Let's have to do 3 loads of laundry. And it takes me 30 minutes to put it in the washing, to do the washing, 30 minutes to do the drying, 30 minutes to fold, and 30 minutes to put in the cupboard. So if I am not particularly smart, I will do a load, that'll take me 2 hours. Then I'll do another load, it'll take me 2 hours. And another load, and I'll do 4 loads, and it'll take me 8 hours.
It'll be 2 a.m.
What?
It'll be 2 a.m.
And it'll be 2 a.m. as you can see from this chart if I start at 6. So I'll have a late night, but at least I got my laundry done. What would now a smarter person would say, well, once I have finished with the washing machine and I've put it into the dryer, and that's what you see down in the lower example, I can already start the next load and put it into the washing machine. And then when the first load finishes from the dryer, I can use its dryer. So since I essentially have 4 units of each being a half hour, and I can use them in stages. How long will that take? Well, the way we count it, look how I count it. I count it as 1, 2, 3, then there's 4 half hours, 2 hours, then 3 more. Then 1, 2, 3. So it's 2 hours plus 1 more hour, 3 hours and a half. So it's 3.5 hours versus 8 hours of the first one. 8 divided by 3.5 is 2.3. That means that the speed up that I'm 2 times faster, or even more, 2.3 times faster. Right? If it would have been 4 hours, then it would have been twice as fast, 2 times faster. But it's even better. It's only 3.5, so it's 2.3 times faster. Now, truth is, this is correct for 4 loads. But what if I had many loads? What if I had 100 loads? Well, it would not remain at this rate of 2.3. Because let's analyze this second case here. In the first instance, I just had the washing machine going. In the second instance, I had the dry and the washing. It wasn't until the last half hour, the 4th half hour, that I had everything running at once. And then I immediately started shutting down things. But if I had like 1,000 or infinite amount of wash to do, then I would be constantly having everything working at the same time. And therefore therefore I'd be having like something in the washer, something in the dryer, something being folded, something you put in the cupboard all at the same time. And I would be getting out, one would be finishing every 30 minutes. Every 30 minutes, another one would be finishing. I have like an assembly line. Every 30 minutes, something would come out. And I'd be using everything at the same time. The problem was that here, for the first 30 minutes, I didn't get anything out. So basically what I'm saying is like this. If we ignore what we call the startup time, and there's a time for everything to start running, and the ending time, where I'm waiting, but I'm only going to get 1, whatever. I'm not using everything in its best way. And I just imagine that everything, in other words, that everything is being used all the time. Because let's say as we approach infinity, then the startup and the ending are irrelevant, go to 0. And the main thing is just when I'm running everything. So then what I can say is like this, that what is the speed up? Well, then the speed up would be 4, right? It would be 4 times faster. Instead of each load, instead of taking me 2 hours, would take me a half an hour. Every half hour I get a load. So that's what we wrote over here. The speed up is 2n, n being the number of washes that I have, in my case 4, divided by 0.5n. Now there's half hour of times per load. And that would be plus 1.5. The plus 1.5 is the startup time. Because in the beginning I had an extra hour and a half where I didn't get anything in. And that equals approximately 4. When we say approximately 4, it means the 1.5 goes to 0 as we have an infinite number of loads. So this gives us a certain mathematical principle that the number of well, maybe we'll see it later, but the more cycles I have, the better. Imagine I had a washing machine, I had two washing machines, one that did the first half of the load, and the other, one did the wash and one did the rinse, each taking 15 minutes. I would take it out from one, put it in the other. Then I would speed up everything and I had two dryers and two folders and two cupboards. So then I would have more cycles. It would take me now 8 steps to get anything done. But each step would be only 15 minutes. And then in the infinite case, I would get something out every 15 minutes. And that's actually the way modern computers work. They actually have many small parts, whereas they divide the process of computing something not into 5 stages, but into 35 stages. And then, well, a large number, like 30, 40, 30, whatever, some 40 maybe, some large number of stages. And each stage is very, very short. And then if I'm going to execute a code of 1 million lines of code, I'll be able to, even though a particular line might take me, let's say, 35 clock cycles to get it done, but my throughput, in other words, the time it takes me to get 1 million done will be 1 million times 1 clock cycle. Because I'm running in parallel, because I'm doing everything in parallel. That's the idea. And that's how modern computers are able to get to work so fast.
What's it 2n?
What is it, 2n? 2n just means 2 because it's 2 hours in our case. And n is how many loads we have, 4. So it's like 8. 8 divided by a half of 4, which is 2. 8 divided, which is 4, plus 1.5 is 5.5. And they're saying 5.5 is like approximately 4. But the point is, they're trying to say it's the number of stages. You see that?
Yeah.
If I have 35,
Stages, it goes.
stages, it'll be 35 times faster than if I did everything like above in no parallelism, just one after the other. It would be 30 times faster if I had 30 stages.
Where'd you get 1.5 from that? I know
1.5 is the startup time because in the first 1.5 hours, 1.5 hours, I didn't get anything out of I didn't get anything ready. And only in the last then I got a half, then every half hour I got something. So it's 2 times n, which is 8, divided by, well, if we ignore the 1.5, which was then it's a half an hour times how many it is. Every half hour I get a new one. So 4 times half hour is 2. So I can do 4. That's the idea. 8 divided by 2 is 4. Because a half times 4 loads is 2. Why a half? Because it takes a half an hour to get a load out. You'll tell me, but the first load takes an extra an hour and a half. So I put that as a plus 1.5, but that's negligible. That's because in the large scale, that would be small. That's how all businesses work, right? If you have to start a clothing store, the first thing you have to do is renovate the shop and the certain startup costs. And then hopefully you'll be making money every day. And eventually, after 10 years, the startup costs are insignificant because you've been making money every day for 10 years. The fact that you have to pay some amount of money at the beginning is irrelevant, assuming your business succeeds. Okay, so there are 5 stages in the pipeline. And they're like in the multi-cycle, but we're going to call them by shorter names, or it's important actually to sort of, I don't know, useful to kind of memorize these names, but these are the stages. What?
If it accident.
Whatever. I wish it would be an alphabetical order. but we're gonna use these
It
names.
X and then.
The first stage is instruction fetch, then the next stage is instruction decode and importantly register read. We read the registers in the second stage. The third stage is execute, which means we use the ALU to, let's say if it's an add, to add the two numbers together. And then stage 4 and 5 are not gonna be existing for all commands. For example, for an well, an add, they will be there, but
Jump.
memory exists, the memory command is essentially for accessing memory. We'll see which commands use that stage. And the write back stage is only for one command, which is load word. Load word or load byte or load half, the load commands are gonna have a fifth stage. So these are the 5 stage. Instruction fetch,
Where would,
instruction decode, yeah.
where would it write to the register if it in like an app mode? Which stage?
We're in an add command, we're right in the mem command, in 4. That's why I said the add will have the 4th stage, even though it's, the name of it is not associated with that command. So now, let's talk more about computers and less about washing machines. Assume the time for a stage is different. For example, registers are very fast, so they're only 100 PS. PS is picoseconds, which is smaller than a nanosecond. Right? 1,000 picoseconds is 1 nanosecond.
How much is that in a second?
A billionth of a second. But it's a whole 100 picoseconds, so it's a lot of time. And that's kind of a joke. These are very small numbers, very small amounts, but anyway, it doesn't really matter. You could replace it with nanoseconds, doesn't matter for the concept. So it's 100 picoseconds for a read or a write because that's very fast. Other stages are 200 picoseconds. So let's compare the pipeline data path to the single cycle. Now, the single cycle has these same 5 stages, but let's look at them. The stages are going to be 200, the register read, in other words, the ID will actually be a faster stage, only be 100. The ALU and the memory will each be 200, and the register write here at the end will also be a shorter stage, it'll be 100. So if I add them all up, I'll get 800 picoseconds. That's to do one command in a single cycle, nothing in parallel. Now, theoretically, a store word would be quicker because it doesn't have this final stage. So we only 700. And furthermore, theoretically, the read write, the R format. So I answered you incorrectly. It's the 5th stage that will be in the multi-cycle. We saw those in the 4th stage, but here we're thinking of it in the 5th stage. It's write register, so that's why the name doesn't reflect it, because it doesn't happen then. It happens in the 5th stage. But in any case, this would theoretically, if we could run this in the fastest way, it would be 600, and this, if we could run it the fastest way, it would be 500. But what are we going to do in a single cycle? We're going to make them all 800. Every command will be 800. Why?
Run in parallel.
No, we're not running in parallel with single cycle. In single cycle, we're running after each other, but we got to choose a clock cycle that's long enough
In everything.
to be able to finish any command we throw at it. So we got to take the worst common denominator. In other words, we got to take 800 because if we take a shorter amount,
We'll finish.
then some things won't finish. We can't change the amount. In the multi-cycle, we could. In the multi-cycle, what would we do? We would say the cycle length would be 200. Think about this. The cycle length would be 200 picoseconds. And then for some commands, we'll do all 5 cycles. It'll be 1,000. It'll be 1,000 because it'll be 5 cycles times 200, 1,000 picoseconds, which is a nanosecond. And some will be shorter because if it's, let's say, a branch, which we finish in 3 steps, it'll be 2 times 2 plus 2 plus 2 is 600. So in the multi-cycle, I'll be able to shorten things sometimes. But in the single cycle, I have to have it always be 800. That's interesting, right? The single cycle will be 800. The multi-cycle will vary from 600 to 1,000. What about the data, about the pipeline? So look at this, so now we got that information here, but we're basically just saying what I just said, kind of, except we're comparing now single cycle to pipeline. Here we have like this, here, let's say we have these commands, load word, load word, load word. We have 3 different load word commands. Each one is going to take, in a single cycle, 800 seconds, right? I mean, every cycle, everything is gonna take 800 seconds. So it'll be a total time of 2,400 picoseconds. Right? Agree? But if I do the same commands in parallel somehow. Now, what I'll have is a situation like this. The first time I can only do one command, I only got the first command, I started him off. Now, before I finished him, I'll start the second command. And before I finish him, I'll start the third command. But now, each of these mini cycles, each of these cycles that are shorter now, which are only 200, they have to all be 200, even though that's why this is a blank here, because this is really only using the CPU. I mean, I'm only doing something in the second half of my 200. I have 200 picoseconds,
right away.
but no, actually.
Like a start time, a start.
Actually,
Wait.
no, we arrange things in such a way that the action happens sometimes at the beginning of if it's a short action, let's say it's 100 and we have a 200 frame to do it in. We choose that some of them happen in the first half and some happen in the second. For certain reasons, we'll see. So
Yeah, you get
It's all on a multi-cycle,
what?
it's all on a multi-cycle chip. And you can't do this in like a,
No, this is a pipeline chip. We're
it's
through
a
the,
different chip.
yes, it's a pipeline chip. So, but well, right.
We're gonna do the beginning half, the second, you know.
It's right now, we're just talking theoretically. We'll see how to actually do it as we go on. But right now, we're just explaining our goal, how to get our goals, everything. This is our goal. Our goal is to have a situation like this where we start this command off. Now, while this instruction fetch of the second command is going, the register, what was it called? The ID instruction decode is happening of this command. And while this is, and while the first one is doing the ALU, then the second one is doing the instruction decode, and the first one is doing instruction fetch. And when he's doing data access, so this is like a certain point in time. Notice this is a timeline. So this is a certain point in time. At this point in time, 3 things are happening at once. This point in time, 3 things are happening at once. Now this command finished after a little bit early, but we can't actually start. We still couldn't start the next command until here, because we're gonna always, because I don't know a clock cycle. But in any case, you see the basic idea? Now, how long is this gonna take? Well, here's the way I count it is, this is gonna take. How long is it taking? This takes 2, 4, 6, 8. 900 or 1,000.
It's like 1,000.
Probably 1,000. You probably don't get the result till 1,000. So it's 1,000.
Yeah. 1,000.
But then immediately after that 1,000, I get another one and another one.
Yeah.
So it'll be 1,000 plus 200 plus 200 is 1,400. Versus the first one, which was 2,400. So it's much faster. Well, it's like almost twice as fast. If we could somehow do this. But the interesting point we're just trying to point out is that like, what if I ask you this question? I want to do just one command. I just want to do one command, that's my whole program, one instruction. Which would be faster?
The single thing.
The single cycle. That's the point I'm trying to get across.
Yeah.
Hey, that's really fast.
So we call that like the throughput. As the time for,
Yeah,
that's the throughput, sorry. We call that the
Why would it be the same?
what?
Why would it not be the same?
Because you have to select a specific amount of time for each command.
No, because we
Register right happened in the second half, to get the way to.
we've decided that the single cycle will be 800, which means every 800 picoseconds we get the result. So when we do one command, we'll get an 800 picoseconds. Why? Because it was 200 plus 100 plus 200 plus 200 plus 100. So that adds up to 800. But but this one, we can't have different size cycles. So they gotta all be 200, even if they're short. So it comes out that we'll take 1,000 for a single command. Okay. Now. Pipeline speed up. If all stages are balanced. Why is Isaac writing this?
Sorry.
If all stages are balanced, i.e. all take the same amount of time. You hear what I'm saying, Isaac?
Yeah,
If, imagine if it wasn't like that, imagine if it was that some were 100 and some,
So then-
not some are 100, all of them were 200.
okay, so then, that's what we just had.
No, if they really, in reality, to execute every single stage was the same amount of time,
Oh,
Will be the same.
then there would be no advantage to single cycle, even for one game.
Yeah.
So then it says like this, the time between instructions in a pipeline version would equal to the time between instructions in a non-pipeline divided by the number of stages. So what do we mean by that? Let's give an example. The time between between getting my result, that's what I mean between instructions. Time between instructions would equal to, let's say in the non-pipeline it's 1,000, right? Time between instructions is 1,000. But if I have 5 stages, then I gotta divide 1,000 by 5 and get 200. And that's what we were saying. In other words, this equation is correct, assuming that all the stages are the same time. Then this will tell us that a pipeline gets an instruction done every 200 seconds,
Yeah, there's a lot of.
whereas the other is 1,000.
There's a lot of assumptions to this equation, it's not like,
What we say, no, one assumption, if all stages are balanced, that's the first sentence here.
Yeah.
If not balanced, so now you say, what if it's not balanced? So the speed up will be less, depending on how not balanced it is. Speed up due to increased throughput, so we call that throughput, how much you can get out, but not increased on, like I said, not necessarily. That a single instruction could be faster. Latency is the time for each instruction does not decrease. What does that mean, latency? The time for a single instruction does not decrease. The
Will
time
increase.
for each instruction
It'll be
does
up to
not,
one
it's like
cycle.
double negative here. Does not increase, means it increases. The
Or-
time
or
for each
stays the
instruction or stays the same, or increases the time between the time for one instruction, that's what I was saying. If you have,
Do the faster.
if it's if they're all equal anyway, then they'll be equal. Because if all the stages are 200 anyway, then the single cycle will be 1,000 and the pipeline will be 1,000 for one instruction.
yeah,
But if, that's what they're saying here, it's equal or greater or increases, the latency, the time for each instruction could increase actually. If, that's what I said, in the single cycle be 800, it could go to 1,000. Anyway, I'm just explaining what's written here. Okay, now. MIPS is designed for pipeline. Some of the things that help it for pipelining are that all instructions are the same length. That makes it easier to fetch and decode. Why does it make it easier to fetch and decode in one cycle? Because if it would be longer, if an instruction could theoretically be 64 bits, then I'd have to do a load and then another load. I have to load 2 registers, I have to load 2 lines of code to get the instruction. Right, if the instruction was spread out over 2 lines, then I would take longer, and sometimes it would take me longer, sometimes it would take me shorter. It's more complicated. There's few instructions, they're all in the same regular format, basically. Load and store address can calculate in the 3rd stage. Alignment, whatever, we'll see what the advantages are as we see. Now, there are 3 kinds of hazards. Now, what you should have been asking yourselves is, how can we use the same hardware to run different commands at the same time? Well, the first command will like be obliterated by the next command. The second command will overwrite the first command. How can you have, things going on at the same time? If you have I don't know, baseball field and a guy is batting and then somebody's practicing throwing to first base at the same time, and the pitcher is throwing, and all the balls, there'll be many balls, and they'll hit, people get hit, and it won't work. You need to have, you can only do one thing at a time on a baseball field.
like the soccer pitch with
It's like a soccer pitch right by my house in Baca. You have I live right next to that soccer pitch, yeah. There's if you have many people playing at the same time, all of a sudden the goalie has 3 balls coming in, he doesn't understand where they're coming from. So so these are called hazards. We differentiate 3 types of hazards. One is structural hazard, which means that we want to use a certain piece of hardware, but it's being used by another command. What's the solution for structural hazards?
Well, another piece.
Add more hardware. In other words,
You can't fix it. You can't fix it without
right,
getting.
data hazards. What about if we have data
Or
hazards?
add time the buffer or
No.
whatever.
Data hazards. Need to wait for previous instruction to complete its data read before we can write.
Shut you down. This is data.
A data hazard is like this. When I
Increasing the.
have
Not that structure.
data that I am writing to, let's say I have I equals 7. Or I plus plus. And in the next command, I use I say that J equals, if you're talking while I'm talking, then I'm just gonna keep talking because.
See, that's structure hazard.
Then I'm gonna have J equals I plus I. Well, if I hasn't finished being updated, when I do the next command, J equals I plus I, I'm gonna get the wrong result. So that's a data hazard. The data that I'm trying to get has been corrupted.
You add.
The third type is a control hazard, where deciding on a control action depends on the previous instruction. In other words, I say I plus plus, and in the next line I say, if I equals 7, then do something. Well, what if I hasn't been updated yet? Now I'm jumping to a new line of code, I'll jump to the wrong place. That's actually the worst hazard. You don't want that. Okay, so we're gonna talk in depth about these hazards. The first hazard is structural hazard. Question?
Yeah, on the decision, what's it called, decision, a control hazard, why is that the worst one? Wouldn't it just be that you have to wait to find out, like?
All of them are solutions, but it's the worst one in the sense that it might throw us to the wrong line of code and then how we have to act. Okay, structural hazards, conflict for use of a resource. Well, that's what I explained. I need the ALU and somebody else is using it. So in MIPS pipeline with the one they're thinking about here is the single memory. If we have a single memory unit to access memory, then what if what if I want to read an instruction and I also want to access memory at that time because it's a load word, because let's say I sent in a load word command and the load word is finally at the point where he is loading the word from memory. But at that same point, I have a new command coming in, he needs to read memory to get an instruction. So obviously I'm gonna need 2 memory units. One specifically for getting instruction. So the pipeline data path requires separate instruction and data memories. Or caches, but the point is, we're gonna need extra hardware. That's just one example. We'll see there's extra hardware. Okay, data, that's the first type of hazard. That's the simplest one. Second one is the data hazard. Data hazard is just like the example I gave you. Look at this example. If I say S equals T0 plus T1, and now the next command is T2 equals S0 plus T3. Well, S0 isn't ready yet. So what I might do is so here's the commands. Here's the add, and here's the subtract, the second. And in between, I insert what's called bubbles. Or you can think of it as delays. Basically, I say, hold off, don't do anything. Or it's also called like a no operation, NOP. I send in a no operation, don't do anything. Of course, I'm gonna have to identify that this has occurred.
Wait, so bubbles like no,
A bubble is saying,
don't do anything.
don't do anything in this
How do you
stage.
send that in?
Essentially, I write no, I tell them NOP. Who is gonna do that? Well, the programmer will have to write NOP as a command. He'll do this command, and then he wants to do the next command, he'll have to gonna write NOP. Or
Complicated.
the machine itself, we'll see. We're gonna learn how the machine itself can determine that.
Could you have the program like put in other lines of code that don't rely on any previous code? You just write something, cool.
Yes, we'll see, that's another solution.
Okay.
Yes.
In the bottom.
But actually, I misspoke really a little bit. That is a solution, but we're gonna learn first how to do it in hardware without the programmer being involved. Okay, so why did I have to put in 2 bubbles? Why not 1? Why not 3?
Seems like
Because.
the S zero is a bubble? What,
The
what's
word bubble, what the thing, the cloud, the word bubble in it is a bubble.
So what was it?
So in other words, remember this should have been the next command. This first bubble here should have been the IF of the second command. Instead, we delayed it all the way down to here. When he was doing the memory. And now. At this point. Wait a second, okay. So this is the write back. At this point, the fifth stage, the write back occurs. Notice, by the way, we have different symbols here. We have
Oh.
a box, instruction fetch, instruction decode, execute. Notice we have a picture of an ALU. Memory access. Why is memory access white over here?
It's not used.
It's because it's not used. We're not gonna do anything in that stage. That stage will be blank. And actually, the command that we wanted to get. Like, let's say we did add T0 plus T1 and happened in this stage in the X. And then it's not written to S0 until all the way over here. So really, if we started at time 0, we should be at time, I don't know why these numbers are not exactly right, but it should be at time 1000. At a time 1000, this should finish, and then we should start over here. Why don't we only start like at a time 1000? We started at time. I don't know what this was. This was time 0. This would be 200, 400. We timed at 600. It's like we started way too early. We started at time 600. And then, well, instruction fetch doesn't matter. We don't need it. But instruction decode, we're already getting it. Instruction decode, we're reading the registers and sending them off to be processed by the ALU in the next step.
Oh, it's the second.
So we read it over here and it was wrong. So why, this seems like we don't have enough bubbles,
We read it.
because we read it and it hasn't gotten written till.
Well, it only takes half of that 200.
Oh, very nice,
That's
very
cool.
nice. So if you notice that this is shaded and unshaded. The
Yeah,
shaded is when it's actually
Right.
happening. But let's wait, don't rest on your laurels, we're going further.
can you explain?
Yeah,
You're saying.
I'm explaining it right now while he's running around distracting the whole class.
What are you doing?
The write back. The write back over here. Actually takes place in the first 100, because if we go back. I think we said. That the write back takes only, look at this, Isaac, I'm answering your question, you're not paying attention.
Sorry.
The write back takes 100 picoseconds, not 200.
Yeah, that'd be said, yeah, sure.
So over here, it actually finished after 100. And it's ready. Now you say, well, wait a second, maybe he'll read it in that first 100. Ah, but the ID stage, look at the ID stage, it also takes only 100. The register read takes 100, but we're not gonna do it in the beginning, we're gonna do it in the end. That's why there was a blank over here.
Yeah,
We're gonna do it in the latter half.
yeah,
So that gives us this amazing ability here, which is that he wrote it in the first 100 seconds. And in that very same cycle, he only starts to read it in the second half of the first cycle. That cycle,
yeah.
and then it's already updated. So it's sort of like these two fit perfectly on top of each other.
So why do you need the two bubbles?
Well, if I don't have two bubbles, then I would have started over here.
Yeah.
And I would be reading it over here when it isn't ready yet, it's still in the execute stage.
The computer has the ability to, even though it's within the same kind of cycle, but to be able to do that. Like within the same 200, what's it called?
Yeah, in the same cycle to do what?
Because before you said it has to wait 200 each time before it starts, it goes on.
Well, we're doing things in parallel, we're running
Yeah.
the washing machine and the
Yeah.
dryer at the same time, so. I can't do this command, I can't, if I was in single cycle, I have to wait for this whole thing to finish.
No, I got that. But even go back, like if you go back to diagram or something, here's more. Yeah, this one. You still have to wait till the 400 mark to start the next thing. Can't, still not like exactly, I mean, it gets parallel, but you still have to wait.
That's because the instruction fetch, I can't start it because I gotta go by the longest length. I
Yeah.
can't start the next instruction after 100 because I'm still in instruction fetch of this guy.
Yeah, got it, so I'm saying, but
So
why,
that's gonna make me, my starting point always be by 200
I got it,
intervals.
why over here is it different?
It's not different. Here, I'm not, it's just that the data happens to be ready at this point. At this point, the data is ready, so my read, which I do, when I actually read it, I'll have the correct data, that's all. It's not that I'm starting the I started the command actually at the same time as this command started, at the 200 point. You know, at every 200 interval, I started this command. It's just I started the command and the first 100 picoseconds, he twiddled his thumbs.
Well, who's being used by the previous?
No, the ID here, command, is just always twiddles his thumbs.
Sorry, that's WPC.
Then you have, if you have commands like that, those two in a row, then it's, you could be more efficient by placing other commands that don't interact with between them.
Yes, so if we were, right, but before we get to how the programmer could solve the problem, we're talking about, what if we have a dumb programmer who did this? And then we, as the processor, want to solve the problem. But you're right, we could also solve it by the programmer. So here is one thing, we somehow have to detect the bubble. We don't somehow have to detect this problem, and the hardware would insert a bubble. I said it a little bit wrong when I said the programmer inserts a bubble. Because it's true that he could, but that's not what's going on here. Okay, now how do we actually do this? Oh, no, sorry, that's the bubble solution. Here is a better solution. A better solution is called forwarding, and this is, or bypassing. And this is a very useful technique. Can you erase that line, Andrew?
Yeah, sorry.
Now, use the result when it's computed. Look what we do here. We say like this. Yeah, Isaac, why you keep drawing things? It's very irritating. Maybe you wanna go take a break and go for a walk.
In a minute. Took a lot.
Okay, so. Here, in this case, we ran the commands exactly at the same time, without inserting any bubbles, and yet we claim that it will work. The same two commands, and how will this possibly work if we didn't delay at all? So look what we're gonna say like this. We're gonna say the first add command, well, remember it had this whole waiting here and the mem where it was not doing anything, and then it was only writing it over here. So why don't we do the following? Why don't we start this command anyway? And then when we read the data, we'll read the wrong data from the register file, because it hasn't yet been written, that's only gonna be over here. So we're gonna read the wrong data, but as that data starts traveling, we realize our mistake. And we go and grab the data directly from the ALU out, from whatever the ALU created. Because the ALU was created something for the previous command. We didn't use it, right, and we're gonna grab that result and put it into the ALU over here. So in other words, it's true that we'll do this we'll do the instruction fetch that way, that's good. It's true that we'll do this ID, essentially this ID will be useless for us. The ID the result of that ID, the instruction fetch and getting the registers, we'll just throw that in the garbage. And we'll instead take directly from the result of the ALU, the value that we actually want, and not wait for it to get written. So now we actually don't have to have any bubbles for this, and this is the way we'll do it. We're not gonna do it the other way. The other way was just like an idea. This is the actual way. Wow. Don't have to have a delay, but this requires having what you might call a short circuit. In other words, in a good way though. In other words, we have to have a shorter way or a shorter path. And that's why it's called a bypass or a forwarding. We're gonna forward the data from here to here. Now, what about a different scenario? What if we have a load word and that's loading it to S0, and the next command is use that S0 and compute something. So what is if the value is not computed when we need it, no amount of forwarding is gonna help. So we're gonna have to put a bubble in here. So look at the bubble. Why do we put a bubble here? Because we can't grab it from. What does a load word do? It reads from memory. It loads a word from memory and stores it in S0. right, that's what it's doing, it's loading it into the register. So we don't need to wait for it to go into the register. But we do need to wait for the memory. We can't grab it from X. What did X do in this command? In this command, execute did, it added together 20 plus the value of T1. And that value is an address. That's not the value we need, so we can't bypass from over here. We have to bypass from after the memory, after it got it out of the memory, which is a whole nother cycle later. So therefore, and we still need to put it in the same place, so therefore we need a bubble. If we hadn't had a bubble here, then this arrow, then this bypass would be going to the left. And that's impossible. That's called traveling in time. Alright,
We can do that.
the arrow must always go forward. That's why it's called forward. Okay. So code scheduling to avoid stalls. This is what I was talking about before. I don't, without dealing with this C code here, but let's say you have the following commands here. Now, notice that I have a load, this one I needed a stall, right? A load word followed by any R type that uses that register requires a stall. We call it also a bubble is also called a stall. So look, here's a load word. And then I use that value in the next command. Here's another load word and I use that. So this is going to require 2 stalls. The other commands don't require the stalls. So how do they get 13 cycles? Well, let's count. The first one is going to take, the first one is going to have all the startup time. So it's going to be 5 full cycles.
Yeah.
And then each one will be, if it would have no stalls, each one would be 1 cycle more. So 5, 6, 7, 8, 9, 10, 11. But I have 2 stalls, so 11 goes to the 13. That's why it says 13. But look here, it's going to be actually 11 cycles, which is the theoretical best possible execution. How did I do it? I simply took I loaded the T, but instead of using it right away, I stuck in some other command. And that command, I use it right away. I need 1 stall. Well, now I got 1 stall because I stuck in another command. And what command did I put in? Well, Dafka, I put in the command that computed that had another stall. That was the T4. I put him there. And now I also immediately got this guy in. I could have actually put this command, this add right after the store word here, right before the store word.
Yeah.
But because I already got the 1 delay over here. So by rearranging the code, I don't need to put in any stalls because the code itself is the stalls. Who is going to do that? Well, the programmer could do that. Or if I wrote in a high level language like C++, so the compiler compiles it into binary and into machine language. And if he identifies these, he knows the hardware that he's compiling for, because he has to know the hardware, because he has to know the instruction set. So he knows where there's going to be a need for a stall. He could rearrange my code. That would be called an intelligent compiler. There are intelligent compilers that do this. So there we have a solution. We don't need to rearrange code for a command like add and then subtract, which is a very common command, right? I added something and then immediately use it. It'll be ready. I won't have to wait.
You do have to read those, no? We've got bubbles.
What? I didn't have to, these bubbles in the end we determined we can get rid of by having a forward.
All right.
So in this command, I don't need any bubbles, and the compiler doesn't need to get involved. In this special command, if I wouldn't have any forwarding, how many bubbles would I need here?
3.
I would need 3. It's essentially 1 worse than this one, and this one had 2. This one had 2 bubbles, and we got rid of it by forwarding. Now this is one we have to forward and get rid of and add a bubble, so if we wouldn't have any forwarding, we'd have to have 3. Okay. Let's go on. Control hazards. Control hazards is like this. The branch determines the flow of control. Fetching the next instruction depends on the branch outcome. In other words, which instruction to fetch is dependent on the branch. That's an instruction fetch is the first thing that I do. So my instruction fetch, if I have a branch, I can't just merrily go and instruct, and I don't even know it's a branch, right? Let's say, I have my lines of code, I don't know, say. Some kind of random lines of code, A, B, C, D. Now, if this one is a branch. And then I just go here, in instruction fetch, I don't even know, well, it's a bad picture, whatever. In instruction fetch, I don't even know what the command is over here. And now maybe I find out, at the end of it, I find out that it's a branch. But I don't know the result until I did the ALU and get the 0. So I've already just started executing the wrong command. So it's a very big problem here. Yeah. Pipeline can't always fetch the correct instruction, still working in the ID stage of a branch when I'm already loading up the next instruction.
Now I have the bubble.
So we'll have to use bubbles and branches too.
Yeah.
Yeah, well, we'll see this, we're gonna see the solutions. For branch, we could get the result early by comparing registers and computing the target in stage 2 in the pipeline. No need to add hardware to do it in ID stage. So that's the first thing we're gonna do is like this. We're gonna say we're gonna add extra hardware to compute the branch result, whether we're supposed to branch or not, already in stage 2. So then wait until the branch outcome determined before fetching the next instruction. So if somehow, let's say this is a branch, see the VEQ, that's a branch. So somehow we added a whole lot of extra hardware in this stage, in this ID stage. That's what's called reg here. It really should be called ID, but whatever. Instruction decode and register read. So in this stage, we're going to add stuff to determine our branch. And by the end of this stage, by the end of stage 2 over here, we'll know where to go. We'll know which instruction. So now we can do the instruction fetch for the correct command. But that was only because that was you have to add one bubble. We have to add one bubble and add a whole mess of hardware to essentially determine whether we need to do a branch and what the location is to go to for that branch. Already in stage
Yeah.
stage 2.
I didn't get that. Okay.
Yeah, well, this is a little bit complicated. Because I'm not showing you how it's done. I'm just saying, let's say we had a magic box that would finish the branch in stage 2. Without update, it wouldn't update the PC, but let's say it would tell us everything we need to know in stage 2. If we had a magic box that would do that, then we could know which instruction to fetch. Problem with the branch is, I'm saying if A equals B, then do this line of code. And if not, do some other line of code somewhere else.
Yeah.
So the first thing, so what line of code should I, it's like if I was washing laundry and I would say like, if the laundry comes out, if I would give the instructions to my maid, you do the whitewash and if the laundry comes out pink, then on the next load, turn the temperature down. Let's say like that. I do the wash, but if it comes out not good, then the next load I want you to do at a different temperature, at a lower temperature. So what's she gonna have to do? She's gonna have to wait for all the cycles to finish, or I don't know, she have to dry it maybe because when let's say she has to dry it, fold it. If it comes out wrinkled after out of the dryer, then turn the temperature down. Or then for the next load, put it in fabric softener. That's a better example. If it comes out wrinkled after the dryer, then put in fabric softener on the first one. So she can't, that means after the first load comes out, she can't put the next load in because I'm telling her, wait till you dry it and see how wrinkled it is, and then that'll determine whether you put in So, so what will we have to do? We'll have to somehow give her a magic box that lets her dry it instantaneously. And then she could run the next command right away. If we could build anything in the world that we could imagine. And allow her to somehow get that thing done quickly. Then we wouldn't have to wait. And that's what we're trying to do here. We're saying like this, we're saying, we'll build, that's what it said in the previous slide. Here. For branch, we could, it's really badly written, we could get the result early. It should say, we will get the result, we will decide to now get the result early. By comparing registers and computing the target. Now, is figuring out where we're going. In stage 2 on the pipeline. We'll of course need to add a ton of hardware to do that.
Is there
And
hard?
we're not gonna tell you how,
Is
and
there-
we're never gonna tell you how, and it would be an interesting homework.
Is there hardware to do that? There is?
Sure, just add another adder, you know, you do all the things that you would do anyway, and just. And somehow add extra hardware and somehow get it done early. Yeah,
We don't even know how to do that.
we don't know how to do it. I say, that's why it's called a magic box. We're just gonna have something that's gonna let us know.
Well, like,
No, this is a big point because. If I wouldn't explain, the truth is you could gloss over this point. Most teachers when they teach this gloss over this point because they did. And then they just say, and then you have to scratch your head and say, well, how can I do the instruction fetch? With only one bubble? I don't even know what, the branch doesn't finish until stage 4. How can I do it here? I should wait even more.
the answer is like.
So the answer is that previous slide said, well, we're gonna add some more hardware and we're gonna somehow magically get the result early.
That's not a satisfactory.
If you get the result early, you don't skip it, once you finish the branch with the ALU, whatever, if you're anyways doing it, comparing it.
Because we still wanna load the PC. That's the one thing we're not gonna do. The one thing we're not gonna do in stage 2 is change the PC correctly. You see what I'm saying? Which is happening in this register write. The truth is, when do we actually know, if we wouldn't add any hardware? Here's a great question, if we wouldn't add any hardware, when would we know whether we need to branch or not?
After the ALU, no?
After the ALU, correct answer. Why not after the reg? Or after the data access? First of all, what happens in the data access in a branch?
We load registers.
No, data access is nothing.
No, data access.
In data access, the 4th stage, nothing will happen in the branch. And when will the PC get written? In register write.
I thought in the branch, nothing happened in the last 2 stages.
That's in multi-cycle.
Uh-huh.
No, the last 1 stage.
Yes, no answer.
Wait, oh, sorry, last 2 stages, you're right, last 2 stages, you're right. Branch is the last 2 stages of nothing, but that's a multi-cycle. Here, we have this thing called reg at the end, that's register write. Anything that required writing to a register, like the PC, will happen in that 5th stage. So the branch won't finally complete until reg.
Why don't we need to wait?
But we don't need to wait till then, we have actually the result after the ALU computed the 0. And also in the previous stage, in stage 2, also anyway, just in case we computed the result of the location to go to. Right, in stage 2, we already compute. Remember, in stage 2, we already computed the address, we used the ALU once, remember multi-cycle? We used the ALU once to compute the address that we want to go to, if it is in branch. We said just in case, we don't know if it's a branch or not. But we'll compute it in stage 2, and we'll know where we want to go, we'll know where,
Where to go with branch.
did we actually read it? Right,
Add it to the PC because it's in a relative address, right?
yeah, we use the ALU over there.
Yeah.
And then we use the ALU a second time in stage ALU stage to determine if the results are 0, or it gives the 0 flag, if they're equal. And that we did in ALU stage. So by the end of the ALU stage, I think we would know.
So what's the?
But what we're doing here, then we'd have to add 2 bubbles.
Wait, so what's the?
Then we'd have to add 2 bubbles. That would be an interesting question on the exam, right? If we don't add special hardware in stage 2, then how many bubbles do we have to have such a case? And the answer is 1 more.
Wait,
That's what I,
One more than if we got more.
two, we need two.
Professor, what, if you can get the answer in ALU after ALU, what's the point of the data access of the reg at the end? You know in the branch of people.
Well, first of all, the reg write, I'm telling you, is updating the PC. That's what a normal branch does, it changes the PC.
Even though the ALU already knows
Yeah, that's just, I have the result, but I gotta write the result.
but for us to do the next.
But what about the data access, when is it? An ALU, a branch has to say,
Why would you need the two bubbles? You could just do the instruction.
the branch computes the result in stage 2, right? It takes the PC. And it adds it to the offset that you gave in stage 2, yeah, so I'm correct. In the end of stage 2, we know which line of code we need to change the PC to. But we're not gonna actually write the PC until stage 5. I was like, we're not gonna actually know whether we change the PC until stage 3. That's when we do the subtraction. And see that it's 0. So all we have to add, only hardware we have to add in the ID stage is an ALU or a subtractor, a special piece that subtracts and tells us the result of the registers subtracted. And then, based on that result, we will decide which instruction to fetch. I'm just saying, I'm giving you the answer. The answer, we'll have the piece of material we have to add is a special subtractor, that's it. We'll add that to the, I said a whole lot of hardware, now I'm thinking about it, and what exactly it would be. It would just be a subtractor, and maybe a subtractor is fat, it wouldn't need a control line because it would always subtract. Right, it would be a special thing that just subtracts and only has one output, which is the 0. And that would be in stage 2, and that would be quick. That would be some kind of quick machine because it doesn't have to do everything, it doesn't do one thing, subtract. And it would tell us the result, and therefore we would know, and we already have the line of code we need, and that would just tell us which line of code.
Yeah, it goes to change the PC also,
What?
doesn't it also, the subtractor has to also change the PC.
Well, I think we can leave the branch. It's a good question. The next command will also have to know about this.
And you have to.
What if there would be another command after this or, for example, here? Which we want to do. How will he know where to go? So yeah, we'll have to change the PC in like stage 2 here also.
So we really are not using the last 3 stages of the branch code.
Yeah.
So really, we're not
We're
doing
just
a
using
pipeline.
Right,
Yeah, but
we're gonna we're hot wiring the car. It's essentially hot wiring, right? We're bypassing, that's what is hot wire? Hot wire is you bypass the ignition and you connect what the ignition would have connected to, you know, there's an on-off switch there. You just you ignore the on-off switch and you just put the wires together. That's what we're doing here. We're ignoring the hardware. Now, wait a second, why not always use that?
What?
Right, then the question could be, why not always use
But
that?
then you'd have a smaller cycle.
Or then you can only branch.
You said that we're keeping all the cycles the same size.
Yeah, yeah.
Yeah, so
All
branches,
of them except for branch.
a branch would write to the PC earlier and
Yeah,
whatever, we'll leave it. I'm not gonna get into that question, it's not in the material.
There's a question about this, when you said, we would add 2 bubbles, why wouldn't the branch be able to do the IF, before the ALU finishes?
No, because what instruction am I unloading? An IF is a
Branch.
loaded instruction. No, but it's an OR. The next instruction that I have to know, I need to know, is it 1 line after where I was or 100 lines after where I was? I can't just load an instruction until I know whether I need to branch or not. So I only know the result, I know the result at the end of the second stage. When this BEQ comes along, the second stage is at time 600. It ends. Only at time 600 can I know which instruction to load. At time 400, I didn't know. At time 200, branch started at time 200. At time 600, I finally know what instruction, so I need a bubble.
Because the original.
If I wouldn't have that special hardware, I could do a bypass at the ALU, where I'm using the ALU essentially to do the minus and to determine what to do. So I could grab that minus, if I didn't have the special instruction, then I would just grab it from the ALU after it's time 800.
Okay.
I mean, I'm explaining more than is written here, but just giving you all the options.
Then we really save. We save time, I don't understand how we save time by that. Because we need to wait,
We didn't have to put two bubbles in. We only put one bubble. Remember I said that the what are these called, control hazards are the most complicated?
it's a,
Okay. Branch prediction. Alright, Isaac, we're going on. Predict the outcome, what about this idea? We still don't like this stall here. This stall is terrible, we want to get rid of bubbles, remember our goal, we're engineers, we want things to go correctly, even in bad circumstances. So how are we get, let's say like this. We should predict the branch. In other words. Statistically, do most branches get executed? Or do most branches not get executed?
okay.
You see what I'm,
I guess it's not.
That's a crazy.
in other words, I have a loop.
No, you see the other line, the line average on, the line after a branch, is it meant to be executed or not?
Exactly.
Hopefully.
That's the
Hopefully,
thing.
that's why you wrote it there.
No, the branch, does the branch usually?
Stay the same back,
You could figure it out for your own goal.
Well, let's think about it like this, let's say I have a loop,
Yeah,
and at the bottom of my loop, I say, have I reached the end? If not, go back to the top.
yeah, so most of the time.
So most of the times, I'm actually executing where the branch is telling me to go.
Yeah,
Only on the last time do I say,
Okay.
just no, the condition is not true, continue on. We should, so you could say that most of the times the branch does get executed. Or you could say, well, it depends how they go, I mean, you could say the opposite, but so that is a possible, in other words, what we're saying is like this.
how about that?
We could guess. This is what we could
And
do.
they write
We just started.
We could start the next command.
Yep.
And then if we see that it was a wrong guess,
Yeah.
then abort it.
Yeah.
And then just call it a bubble.
Good, I think we're all on board with that.
Call it a bubble. How do we call it a bubble, by the way? How do we change a command into a bubble?
Garbage.
Yeah.
How do we turn it into a bubble?
We could write in the piece.
Change some wizard.
Whenever you go back and change the command is still there.
Turn off like the enable.
Exactly, turn off all the control lines, set them all to 0. Don't allow anything to be written. So the command will merrily go on its way, but it's shooting blanks. I can't do anything. Okay. So, prediction. So here we say like this, predict the outcome of a branch. Only stall if prediction is wrong. In mixed pipeline can predict that all branches are not taken. Well, that was the opposite of what I said. You can predict that the branch is not taken and that you just do the next line. Fetch the instruction after the branch with no delay. Well, that's actually the logical thing to predict. Why is that the logical thing to predict? Because that you can predict, like that you can know right away what the next line is.
Yeah.
You don't really know what the branch location is until the end of stage 2 anyway. So better predict that it is the next line, because that's the only thing you can predict.
So when we're programming.
So just fetch the next instruction. And then throw out the instruction if wrong prediction. Yeah.
So when we're programming, we should assume, we should make it so our branches are more likely to not activate. Like, we shouldn't do loops based on the branches always activating in order to be more efficient.
Right, we should have a jump,
Yeah.
we should have a,
If
we should have a branch. Which tells me to skip over the jump.
Yeah, exactly.
And then we should have a branch and then a jump. The jump tells us go back. That's not a branch. That tells us go back. And the branch here tells us to skip over the jump. And that only happens once. So most of the time, it'll just do the next line, which is to jump up. And sometimes
And the jump is
And-
not, it's not, doesn't take that, doesn't take.
jump is the fastest command there is. Yeah, jump is.
It doesn't, it's,
Oh,
like you wouldn't get anything.
you're right. The jump is an interesting question. What about a jump?
Probably wait till that last. Like
It's a
branch
good
doesn't do
question.
anything
I
until-
actually, the book does not talk about jumps. I'd have to sit and think about it, but
Jump probably does everything like stage 2 or maybe it's like stage.
well, we
one.
said jump takes 3 stages before.
But maybe in Python,
Maybe it'll also,
they hotwire everything in stage 1.
well, right, we don't even know it's a jump, it's still stage 2. I don't see how we would we'd also have the same problem with the jump, right? We don't know, but, right, we would start loading the next command after the jump,
We could just,
and then we'll have to throw it out, we'll still have to throw it out, doesn't really help us.
So you kind of loop backwards, I have no idea. Just-
Anyway, I'm just teaching you the idea in general is that you execute the command, and if you got it, at least you're right 50% of the time. Why put a bubble in every time and get it wrong every time? Put the command in, and sometimes you'll be lucky. It's actually.
Or figure out how many times you have wanna loop and then don't loop. Just-
Okay, MIPS with, now you're all gonna say, this is not right, don't write loops, just write everything.
and it's more efficient.
It's more efficient, it is more efficient. More efficient, if you have, it's true, if you have, it's actually true that if you would have, let's say, like. Just a loop for two things,
Yeah, for a constant amount of things.
if you know that it's a loop for two things or three things.
Yeah. Like, that's great for 100 things.
Better
It's
to copy paste.
copy paste.
Impossible to read code, but it's like as fast as I can.
Okay, so let's go on. So now so now we're talking about this prediction idea. So let's see if we can understand this diagram here. We have an add, and then we have a branch.
Living with prediction not taken, I thought you are doing prediction.
But as if it's correct. And
This
that's-
is, it doesn't matter, the prediction is that. Can predict that all branches are not taken, which means that we do the next line. Which means, but now we're over here and we're predicting that we're gonna do the next line, so we're gonna do this line and not go to wherever this branch is. Which, where is this branch? 40 lines down the road. So it's some way down. So if our prediction is correct, then we'll just go merrily on our way. See what I'm saying? We got it lucky, we were lucky, we predicted that we were not gonna take the branch. And we're gonna do it, we don't know bubbles, all is good. What about in the same case, but our prediction was wrong? We need, notice that they have this arrow, it needs to tell us if we jump down 40 lines. Because that's what this branch means, or actually not 40 lines, 10 lines. No, 40 lines, it depends, yeah, 40 lines.
You need a lot of,
Remember the compile, the processor
Yeah.
will add, will
but
multiply.
wouldn't you need a lot of bubbles until you get it right? And it's gonna keep.
No, we already said that if we're wrong,
Yeah, then you bubble. it
then
out.
we'll just bubble out this command. We basically, this picture is a little bit not
Okay, but then.
accurate.
but then you
Really,
never
what you
got
should
to the-
see here is a load word going on in
Then you
stage
never get to
one.
the, then you never get to the line 40. Like you never go to where the equals want to jump to,
Why not?
because you bubbled out the command, you don't know what. You predicted it indirectly, so you.
I
bubbled
predicted
it.
this load word. I started executing this load word
Sure,
over here.
yeah,
Now, this box really should say load word.
Yeah.
And then the next box should say bubble.
okay, but you predicted it incorrectly.
But then by the point that I figured it out over here on my branch, by the end of this reg here, I figured out that this was wrong. I blanked him out, now I know where to go, and I fetched the correct instruction 40 lines later.
Yeah.
And that's why it's or and not a load word, okay? I predicted it, I found out the true result, and now I can actually load that command. And this command will start off correctly, incorrectly, and then become bubbled out.
But if it's like too late, is that just, how do you? Right, like
It's
it already
only the
rests in
second
memory.
stage, and you don't change anything in the first stage.
Yeah, we don't change anything, oh, we do change the PC, but that doesn't matter because
We're changing it again.
we're gonna change it again.
So then the jump has to, the branch has to take account for that. So the PC has already changed.
This is kind of,
It doesn't matter.
this is kind of really similar to the concept of kind of.
Oh, I see what you're saying. If the PC is changed. We have to get the old PC, right?
Yeah.
But it has to know that if it's.
No,
Because if we already started executing the load word,
no,
then we finished one box of the load word, we've already upped the PC by another 4, and it's gone up by 8 now.
but
And we assumed it's only gone up by 4, so we'll have to take the old value, but it's only at the end of that command, we're using the old value.
Yeah, we're using all that.
We're using the old value. Okay, more realistic branch prediction, okay, so see, basically up till now, we've shown that we don't have to have any bubbles. And now we have one bubble, and we're really aggravated about this bubble. So we don't wanna have it, so we say like this, static branch prediction. So we could, in other words, the question is, I think the question is actually, are we gonna predict? This is what I was talking about, are we gonna predict the branches that are not taken or they are taken? So based on typical branch behavior, example, at the bottom of a loop, if the branch is to an earlier address. assume we'll go there. If to a later address, assume we don't go there. In other words,
Oh, it's after.
because most of the time the loop is going up and up and up. But if it's jumping, if the branch is a branch saying skip over the jump and go to a later address, then that's only gonna happen rarely. So if the branch is to an earlier address, then assume we do go there. If it's to a later address, assume that only happens once in the loop. And therefore only, don't predict that. In an if else, assume you go to the else. Because an if is just saying, if it's this unique case, then do this, otherwise do the regular case. Dynamic branch. Hardware measured, so here, this is like very complicated. You would have hardware that would measure the actual branch behavior in this particular program. And record recent history of each branch. And assume future behavior will continue the trend.
That's pretty cool.
When we're wrong, we'll stall while refetching and update the history. We must ensure that instructions follow the wrongly, that instructions following the wrongly guessed instructions have no effect, and that's what I was explaining to you about zeroing out the control lines.
Yeah.
Okay. Fine. Although I still don't understand, they didn't deal with the question that I said, which is like, how could we jump to the branch place without having known it yet? I don't see how we could do an instruction fetch.
No.
In the state, when only stage one of the previous command has been finished.
You can't.
I don't see how we do instruction fetch of anything other than the following one. I don't fully
You
understand,
said,
maybe next year I'll understand.
no, but you said,
We could have.
You said that wouldn't work.
First
I
stage.
said that wouldn't work.
I don't understand how it could possibly work, because at the end of stage one,
Yeah.
we don't know. Even if we don't know, we haven't yet computed what the branch in place is, we do that at the end of stage two.
It would be
It is
total guess.
We could, how are the stage
Yeah.
one, right?
Can't guess, jump 100 lines
Yeah,
forward,
it'd
jump
be total
20 lines.
guess.
But it's just part of the instruction, it's just the immediate, we can kind of calculate that in stage one still. We add extra hardware. Right?
We're gonna add it to the PC, you're saying, oh, without we know, it's just 4.
What?
Uh-huh,
Not
I
like-
hear what you say, okay, you're, okay, you're saying we've got it in the immediate value. We've got a 40 over there.
Yeah.
What we need to do is shift it to.
Yeah.
And add the PC to it,
Yeah.
and we could do that in the first stage.
Yeah.
That's what you would have to say, that we'll do that in the first stage, well, anyway, we're adding the 4 to in the first stage.
Yes.
Are we shifting it in the first stage? I'm not sure, I don't remember. We do have a shift, what?
What's the solution? What's the?
What's your telling me?
Nathaniel.
Nathaniel is proposing how we could do in the first stage to get the right address. He's saying, well, basically, it's just the immediate value, plus the PC. And we're anyway, we could add those two together and know where to go. So that we could actually know where to jump, we'd have to shift it. We'd have to shift it and add it to the PC, which we have anyway. And it's all just immediate value, you don't have to even you don't really have to write any registers, you have to just read a register, read the PC, that's pretty quick anyway. We're doing it anyway, exactly. So we could actually do it, okay, but it needs to be, it's not spelled out here.
Yeah.
That it has to be done in the first stage, okay. Delayed branching, another approach used by MIPS. Is to take a safe instruction from before the branch command and place it after the branch command. While the safe command is executed, we are effectively waiting for the branch to complete. By safe, we mean a command that has no side effects of the branch execution. Right. In other words, basically it's saying that, I think it basically means, I don't know if what it really means is that the programmer, I don't think that I don't know how the hardware could determine this.
Yeah.
I think it's that the programmer will put a safe instruction, and in fact. There is in the simulator, you don't do this, but it's because it doesn't have delayed branching, even though delayed branching is used by MIPS, as it says here. If you have a button in your simulator to turn on delayed branching. And if you turn that button on, then after every branch command, you've got to write an NOP, no operations, or some other safe command.
Isn't it just bubbling?
It's human bubble, yeah.
Because that's what we already decided is we don't want to.
Right, but you can put a safe command there. In other words, if you turn on delayed branching, then the programmer is supposed to know that, and then the programmer has to put after every branch. Some safe command that won't have any effect, like for example, he could increment his counter. After the branch. And then instead of before the branch, and then. If it turns out that we're at the end of the loop, then I don't use that counter anyway, I'll reinitialize it later. And if I do go back up, then I've updated, and assume that the command after the branch gets executed no matter what. But then you have to be a program, and then the program would learn certain tricks of the trade. In other words, he'd have to know what he's doing and he develops certain customs. That's not the way the simulators works, okay. The big picture, okay. Summary, pipelining improves performance by increasing instruction throughput. Executes multiple instructions in parallel, each instruction is right, each instruction is the same latency. Between the time it takes. Subject to hazard structural data control. Instruction set design affects complexity of pipeline implementation, right? Right, we made commands, but that we didn't really talk about, but we made commands that are simple and it maybe makes the pipelining easier. Okay. Let's continue. Now we are actually talking about how we're, that was all just like what we want to do. Now we have to talk about how we could do that. Actually, you know what, let's take a break here.
How long are we going to go? Because there's Mars at 8.
Okay, we are back and we're talking about. The MIPS pipeline data path. Now look at this. This is, let's look carefully at this
Yeah, we all.
Diagram.
We all have the same.
what do we see? We see anything interesting?
There are 3 ALUs. Or
Well,
two
no,
add-ons, two add-ons.
Two added, well, we don't see the controller here.
Yeah,
But we see that there's instruction memory and data memory. If, what does this remind us of? There's two adders, ALU.
Looks like
If
a
you had,
cycle.
which, exactly, this looks like the single cycle.
Yeah.
It basically looks like, why does it look like a single cycle? Because the single cycle has the most hardware. So we also want the most hardware. We want to use a lot of hardware because we want to be able to do things in parallel, so we need a lot of hardware. Oh, yeah, admit. Okay, thank you. So. Now, these blue lines, what do these blue lines indicate? Why are some lines blue?
Are those the cycles, the amount of time it takes to get there?
No, the blue lines indicate that it's data from like another time. This data is only, even though it's even though this blue arrow is over here, it's not actually getting there in the first cycle of the first command.
Oh.
It's getting there from, it's getting there in the memory section, in a memory moment of the first command, then finally it gets there. In other words, anytime the line goes backwards, it's blue. But basically, what do these dotted lines mean? These dotted lines mean that we never saw this before. The instruction fetch phase is everything, all the hardware for the instruction fetch phase is before this dotted line. So I'll take the PC, I'll get the instruction, and boom, I got the instruction. I'll take the PC and I'll add forward to it, boom, I got the thing. And it happened, and notice the error goes all the way back to this multiplexer, and whatever, the multiplexer will decide to write it, fine. So that already happened in the first stage. And then in the ID stage, I'll do the sign extend and the reading of the registers. And then in the third stage, I'll do the ALU processing, and I'll also add the sign extended. Well, what am I doing here? This is for the branch. This I sign extended for the branch, but I still needed to shift it left and add to it. What did I add to it? The PC, because it's relative to the PC, and then I got the branch result. And then I'll finally write it back over here, depending whether I need to.
Is this not the
But
single?
I'll do the writing back in the memory stage.
This is, how is it different than the single cycle?
It's just not, it doesn't look any different. It's just that we have taken single cycle and we've put these dotted lines in here, which are very important. But they're telling us what is the stages that are things that are happening. I mean, it's basically the same in the single cycle. In the single cycle,
Same
it
time.
would also be like, it would also be in these times.
The single cycle was just running at the same time.
Yeah, I mean, this is just introduction, we didn't get very far.
Okay.
This is just. Right to left flows lead to hazards. Right, whenever we have a right to left at the blue line, that could be a hazard. Because because it's the wrong date, anyway, fine, let's continue on. What we're going to do is. We're going to add special registers. Why are we gonna add registers? To hold information produced in the previous cycle. In other words, this PC value. Is gonna be computed and gonna be put into this register, this long purple register here. Because the next cycle will already be coming through and he'll get a PC +4. And the next cycle, each time a new command comes in. He'll be running this first stage again. So, let's go slow. So, what we're saying is that there's a big register here, and it's gonna contain two things. The PC and the instruction. And then there's also a big register here, it's gonna contain the PC. And the RS and the RT and the sign extended 16-bit. And there's a big register here, it's contained the result. The branch result, the branch, like where I wanna go in my branch. And it's gonna contain the 0 field, whether it was, by the computation, it's also gonna contain the ALU out, if I did an add. And it's also gonna contain the RT value. Etc., etc. Each time I go to a new cycle, essentially, if I'm, let's say, or we'll see in the next picture, I think, but. Maybe a few pictures later, but I'll say it right now. Basically, if the first instruction came in, he was over here, he was all alone. Then the first instruction moves over here, and all of his data is in this register. For him. And then when that first instruction moves over to here, all of his data is in this register. In other words, he'll never need to reach back and get data from all the way over here. If he needs the PC, he's got it right here in this register. And that means that all of this part of the machine is not being used by him anymore. And therefore other people can use it, overwrite things, do whatever they want, and it won't, he's got a backpack on his back, and all of his data is in that backpack, and he travels with it. So he doesn't need the hardware, anything that he's passed, he no longer needs it, because all his data is here. We're gonna discuss what data he has and why. Yeah. Okay, cycle by cycle flow of instructions through the pipeline data path. Single clock cycle. Oh, it's pipeline diagram, in other words, I don't know what it means by that, but it's like the single cycle, I guess. You say, shows pipeline uses in a single cycle, okay, yeah, multi-cycle, there's two different diagrams. There's a single clock cycle diagram and there's a multi-clock cycle. We'll look at single cycles for load and store. This point is that two different kinds of diagrams. We're gonna look at both of them, but let's just go on. Okay, so this is what he called single clock cycle diagram. Which means that I'm taking the hardware and I'm looking cycle by cycle what happens. So this is the IF, instruction fetch. The PC is read, I do the add, and it gets written into this dark purple area here. The instruction memory is read and it gets written into this dark area here. Let's go to the next slide. Now, what happens is in this cycle, I read from this register. Now, what's going on is like this, that I read from it before this instruction writes to it. This instruction hasn't yet written to it, because otherwise it would obliterate what I've got there.
It's like a delay.
There's always the read happens before the write. I read from it, and by the end of this instruction, if there's some other instruction over here, he'll overwrite it. But at the moment that I'm in this instruction, I read from it. And notice instruction G code, look where he puts this line. This line is going right down the middle of this register. Because I'm reading in the middle. In other words, I'm reading first. And then I get my registers and I write. And then again, I read and I write. And again, I read and I write. And what about the write back? Notice we just had 4 stages. If we go back again, we have 1, 2, 3, 4. Where's the 5th stage? Well, the 5th stage is
Outside.
here. You can see why look, here he wrote that I'm reading. What about writing? I didn't write. The 5th stage is here. I write, but look, I'm going back in time. I'm sort of writing to,
Thank you.
sure, I'm writing to some other, I'm writing to this register file. Now, there's a quick problem here, because there's a different instruction that's sitting over here, right? Who is reading from this
While you're writing.
while I'm writing? So who's gonna get the right data? So the answer is, what would you say?
Read gets.
He'll
first.
read first and then I'll write. So we're both, so in other words, while I'm writing over here, there's some other instruction that came later that's reading, but he's reading the data before I write.
Alright,
Are we not finishing?
I don't have anything for Mark.
Yeah, oops, what time is it?
It's 8:16.
Oh, it's 8:16. Okay, so we'll stop here.
Thank you.
Okay.
I just confirm that it's not writing while the other side, while the second is also writing.
Stop.